Hello! Today we're diving into a classic guessing game, but with a twist. We'll implement it in plain Rust programming language, then take it on-chain with Anchor framework, and in the very end, compare it to the raw Rust Solana program. This is a well-known example for beginners, but it covers a lot of essential concepts. So our number guessing game is the simplest version of the bulls and cows game, where the player tries to guess a secret number. Each guess is followed by feedback. If the number is correct, the game ends. Otherwise, the player is told whether their guess is too low or too high. The goal is to guess the correct number in as few attempts as possible, usually within a limit. Whether you're a station or only exploring smart contract development, this video will give you a side-by-side look at how logic, state and structure evolve across these platforms. Let's get started. Let's start by creating a new Rust project, and we'll name it Guessing Game Rust. This sets up a basic Rust workspace. Inside the root folder, you'll find a cargo toml file, which contains metadata and dependencies. Here's what it looks like initially. And to generate random numbers, we'll use the rand crate version 0.8. Inside main.rs, we import the required libraries, and rand is one of them. Then we generate a random number between 1 and 10. This creates a secret number the player has to guess. Thread RNG method gives us a random number generator local to the current thread, and genRange produces an integer between 1 and 10, but with the upper bound of 11 because it's exclusive. Now let's build the main game loop. To read user input from the terminal, we need to use the std.io module. This module provides various functionalities for handling input and output, and we will use it to read the numbers input by users. We initialize an attempt counter and enter a loop where the player can make guesses. To store the data input by users, we need a variable, so we declare a mutable string variable named guess and initialize it as an empty string with string new. This variable is mutable as users may input data multiple times, causing the variable's value to change. Next, we use the stdin function from the std.io module to capture input from users into terminal. The readLine method reads the text input by the user and stores it in the specified variable. This method returns a value of the result type that can be either OK or error. And expect method is added after the readLine call for the case if an error occurs while reading the input. Then the program will stop running and display the error message. When users input data, they might accidentally include spaces or newline characters at the beginning or end. Therefore, we use the trim method to get rid of these unwanted characters. And then we call the parse method, specifying the type to convert the string into U32. Since the pass method's conversion of the string to an integer type might succeed or fail, we use a match expression to handle each possible outcome, OK or error. If passing fails, we continue the loop, prompting the user to re-enter. Here we increase the attempt count. Next, we compare the guess with the secret number. We will use this CMP method and ordering from the std library to implement the comparison functionality. CMP method is generic and can be used to compare various types of values such as integers, strings, floating point numbers, etc. The CMP method returns ordering less, equal or greater, and we respond accordingly. After 10 failed attempts, the game ends. And cargo run, and the game is ready to play. Oh, we're lucky today. Okay, let's try one more time. So we see how it works. Now that we've implemented the guessing game in plain Rust, let's take it on-chain using Anchor, a framework for Solana that simplifies program development with a Rust-like experience. Anchor init, and name of the project is Guessing Game Anchor. This scaffolds the project structure with built-in support for Solana, pre-configured dependencies and testing. The most important part is librs, where we'll write our program logic. Here we import the required libraries. We need to import the Prelude module of AnchorLang. It contains the key modules and functions of Anchor that we'll need for our subsequent development. This import gives access to Anchor macros, types, and helpers. On Solana, each program has a unique address known as the program ID. This ID serves as a unique identifier for the program on the chain, making it easy to locate your program. In the Anchor framework, we use the declare ID macro to specify the on-chain address for the program. When you first build an Anchor program, the framework generates a new key pair. The public key of this key pair becomes your program ID. You can replace this with another program ID running Anchor key sync command. The program macro is used to define a Solana program module, which contains the program's instructions and other related operational functions. Inside this module, we will write the core business logic. Declaring it as a pub module ensures that the functions within it can be accessed and used externally. Use super allows us to directly use all components defined in the parent module without needing to declare them again. With this, our program initialization is complete, and now we're moving on to writing the program's random number generation functionality. We're going to write a function that returns a U32 type integer. This will be our random number. And now we're going to import the clock module from the Solana program library, which allows us to fetch the current Unix timestamp from the blockchain. The clock module gives us the current Unix timestamp, which is the number of seconds since January 1st of 1970. In the next steps, we'll use the timestamp to generate a simple pseudo-random number from its last digit. It's important to understand that in Solana development, unlike regular Rust, there's no random crate we can just import. That's because blockchain programs are deterministic by design. Every validator must deterministically reproduce the same output for a given input, or consensus breaks. So how can we generate randomness on a chain where a determinism is required? In Solana, cryptographically secure randomness can be achieved through a few different stages. As you can see from the table, the clock-based approach isn't safe for production. It's predictable and can be manipulated by malicious validators who have some influence over block timestamps. So if you're building a serious game, lottery, NFT raffle, or any contract where users could exploit randomness for profit, you should look into VRFs like switchboard or off-chain randomness via secure signed instructions. But in this case, the educational guessing game we're working on, the clock method works well because it's simple to understand and implement. It doesn't require CPI, cross-program invocation, or oracles. It's good enough when security isn't a concern. Also, working with timestamps is useful for other common programs tasks, such as enforcing timeouts, deadlines, or scheduling, so it's still a great topic to learn and practice. Now, back to our function. We call clock get methods to obtain the clock instance. If it fails to obtain, the program will stop and display the error message. We obtain the last digit of the current timestamp by taking the modular of the timestamp and then convert it to U8 type. To ensure the random number is not 0 and is within the range of 1 and 10, we add 1 to the obtained number. And then we convert it to our return type. We need to create a structure named guessing account to store the numbers recorded by the game on the blockchain. Account macro defines the structure as an account type, enabling the structure to map to an account on the blockchain, store the required state information, and be accessed and modified through functions in the program while automatically handling data serialization, deserialization, and validation. In this struct, we'll include a field to store the number. Also, we need to add derive init space macro to automatically calculate the required space during initialization. Moving on to the account context struct that will contain all necessary account references needed for the execution of the program. First, we define the struct using the derive accounts macro, which transforms the struct into a type corresponding to blockchain accounts used for storing and manipulating game states. And we don't forget the lifetime parameter, specifying the validity period of the references within the struct. Now we add the payer field, which represents the payer account required for executing the program. The mute restriction indicates that the payer is a mutable account reference, as the account state may be modified during contract execution, like deducting fees. Our payer is of signer type, representing the entity conducting the transaction. Next, we add a field named guessing account to the account context. Here we see info again, a lifetime parameter, ensuring this account reference is valid throughout the entire account context structure's lifetime. And guessing account is the type parameter that specifies the data type this account will hold. We've set it earlier. Here we also use the account macro to configure various properties of guessing account, such as initialization method, space size, and pay account. Init, if needed, instructs the anchor to automatically initialize the account when needed. If the account is not yet initialized, anchor will initialize it based on other provided parameters, like space and pair we're setting up next. If the account already exists, the initialization step is skipped, saving resources and improving efficiency. On Solana, the storage space for accounts is limited and needs to be allocated in advance when creating the account. Therefore, we need to explicitly specify the size of the storage space required for the counter account. The storage space size needed for the account data in this case is 32 bytes, which should be sufficient to hold all data in the guessing account. And as we've added derive init space macro earlier, we now reference it as guessing account init space when allocating account space to let anchor automatically compute the required byte size for our account. Pair equals pair specifies the pair account, and we're storing the game state in a PDA, program derived address, meaning the program itself, not any user, owns the data. This is ideal for shared state logic and ensures deterministic updates. Anchor takes care of the PDA validation and signature behind the scenes. The program generates the program-derived address PDA from the program ID, seeds, and bump. And now we're adding the system program field that represents a reference to the Solana system program, which is a core component of the Solana blockchain, and it provides essential low-level functions like creating and managing accounts and transferring funds. And now we're going to implement the business logic of our initialize instruction. CTX accepts a parameter of type context, account context, representing the current program context. This instruction returns a result type, which indicates that no value is returned on success, while an error situation will return error. This line of code obtains a mutable reference to guessing account, allowing us to modify its state. This way we can set the number parameter that guessing account is supposed to record. OK indicates the initialization has been successfully completed and returns empty tuple. Next, there goes the guess function, comparing player's guess with the target number. You've seen this logic already in the first example. It's exactly the same comparison using CMP and match. The only difference is that now we return custom anchor errors, including the error macro. This function handles the core logic of guessing game. It compares the number provided by the user with the target number stored in the guessing account. These errors are defined in your error code enum, like so. Now we need to handle the custom errors defined in the error code enum. This makes it easy to return clear, readable, and structured errors that client applications can handle. And if the numbers are equal, if the guess is correct, we return OK, indicating success. The guess was right. Anchor build. To interact with this Solana guessing game program, you would typically or client written in Rust or TypeScript to send two kinds of transactions. One to initialize the game, by creating the PDA and generating a secret number, and another to submit a guess. The guess instruction would compare your input against the stored number and return a message, too small, too large, or correct guess. While this kind of interaction makes the game playable on a local validator or DevNet, I won't cover this kind of demo in this video to keep the focus on the code structure. And now let's take a quick look at how this program is implemented in raw Rust lang for Solana. This way you can clearly see the difference compared to the Anchor framework version and appreciate just how much work Anchor framework does behind the scenes to simplify the developer experience. The Rust Solana program starts with inputs, obviously. Then we're defining the program entry point. Every Solana program must declare a single entry point. Here it is, process instruction, the function that gets called when the program is invoked. Next, we need to define and pass instructions. We need to distinguish between different actions: initialize, create the game state, and guess, submit a guess. We use an enum with Borscht, a compact binary serializer, to represent instruction data. Borscht is needed to pass inputs from instruction data. Next, there goes the game state account structure, as we need a place to store the target number on chain, and a simple struct with one U32 field, which is the correct number. This struct will be stored in a PDA and serialized with Borscht. This structure is very similar to what we've seen in Anchor example. And this constant is used as a seed in findProgramAddress method to derive a unique and deterministic PDA. Next goes instruction dispatcher, where we route the incoming instruction to the appropriate handler and deserialize instruction data into the enum and match it to call the relevant function. Next goes initialize handler, which verifies that the correct PDA was passed in, calculates the rent exempt balance, calls invoke sign to create the PDA account owned by this program. As every Solana account must be funded, rent exempt, and owned by the program, we want the game state, the secret number, to live in a secure PDA, and generates a random number and stores it. I'm reminding you that this approach is not secure and should not be used in real money games. Next, we see the guess instruction that verifies PDA ownership, deserializes the game state, compares the player's guess to the secret number, and returns different custom errors depending on whether the guess is too small, too large, or correct. So now you have the idea how much work Anchor does for the devs to simplify their workflow. Anchor automatically handles serialization and deserialization operations and generates account-related operations. It also ensures that the necessary security checks are in place for safe program execution. Thanks for watching. Bye!